Gerald Miller, professor of physics at the University of Washington. I did my undergraduate work at City College of New York and my graduate work at MIT.
And then how did you get interested in research in the first place?
It took me a while, but I guess in my junior year of college, decided to do what was called an honors project or something like that. And at the time, I guess, well, it's a long time ago, so I don't exactly remember what my motivations were, maybe just to get a good grade or something. But then I started to really like it rather quickly. So there was basically some professors in my undergraduate school who were doing research, and I could work with them. So I started out working in thermodynamics, and the next year I went into nuclear physics. I did some project in nuclear theory. I really liked it. And then it was only in my senior year that I decided I wanted to go to grad school. It was pretty late because I wasn't sure what I wanted to be when I grew up.
Yeah, okay. And then in terms understandable to a high schooler, could you give me an overview of your research?
I'm assuming everybody's heard about an atom. Stuff is made of molecules, and molecules are made of atoms, and atoms are made of electrons which circulate around a much smaller object called the nucleus of the atom. And the nucleus of the atom has positive charge, and the electrons outside have negative charge, and there's an attractive interaction that pulls them together that makes an atom. But now, if you look in detail at the nucleus of the atom, it has protons, which have positive charge and make up the positive charge. And it also has neutrons. And if one thinks only about the interactions I mentioned, it's called the Coulomb interaction, the protons would push each other apart because like charges repel and unlike charges attract. And so the nucleus should then fall apart if that were the only force that was involved. And so there must be another force, and that force is called a strong interaction that holds the nucleus of the atom together. And that's what I study most of the time.
That's really cool. And then what were some of your most significant findings or publications?
There's a symmetry relating the forces between protons and neutrons. If one forgets about the electromagnetic effects, that's like the Coulomb interaction. There are similarities between the interactions between two protons and the interactions between two neutrons. They're supposed to be, in certain situations, exactly the same in the starting theory, but there are small deviations. And I wrote down several theories involving the small deviations from perfect agreement, which were checked out by experiments. It's important in physics, in my opinion, to do things that can be checked out by experiment, either predict experiments, explain experiments. So these things were checked out, but there was an underlying reason for all of the effects that I found. And that is that the answer depended on the structure of the protons and the neutrons themselves, because protons and neutrons are made of objects called quarks, and the proton has two quarks with a charge of two-thirds, and one quark with a charge of minus one-third. So you get the charge of the proton by saying you have two times two-thirds, which is four-thirds, and the other one has minus one-third, so that adds up to one. That's the charge of the proton. And the neutron has two charges of minus one-third and one charge of plus two-thirds. So you get minus two-thirds plus two-thirds, which is zero. These quarks, though, have a mass difference. They almost have this exact same mass. They have to have almost the exact same mass because the protons and neutrons have almost exactly the same mass. But it turns out that the down quark has a mass that's greater than the up quark, and that this effect persists in many, many different situations. So that I think is one of my most important ones.
That's really interesting. Like, I didn't know that you could have a charge one third on something.
Yes, it's one of the great mysteries of physics of exactly why that is so. We have theories that incorporate that, and people can make very detailed calculations. But the underlying structure of matter, as we know it, is that neutrons and protons are made of quarks. And that was actually only discovered in 1965. So relatively new discovery. It wasn't hundreds of years ago, like many things.
Yeah, okay. And then what were the biggest challenges that you faced in research and how did you overcome it?
Assuming that you have time and a job, that's a pretty big challenge to overcome. But assuming that, the biggest challenge is that you want to do something new. And to do something new, you have to do something that hasn't been done before, which means it's hard. And so the biggest challenge is not to give up. If you encounter a problem, keep trying until you solve it. That's also the fun of the field. So the challenge is fun. And if you don't have that attitude, then maybe doing science is not for you.
Yeah, okay. And then what do you enjoy most about your research?
Just doing it, I like to solve interesting math problems that relate to physical situations, and I just like to do that. I'm just fooling around with equations all day long on days that I don't teach or have other responsibilities.
And then which person or mentor in your field has made the biggest impact on you?
There were several. Actually, the first one was my gym teacher. I was having trouble doing certain sports in gym class, and he insisted to the whole class that we just, it's the same thing. Don't give up, keep trying. So that was one main thing. And my thesis supervisor in grad school had a major effect. It's hard to say. I wasn't really close to any of my undergraduate professors. When I did a project in nuclear physics in undergrad school in college, I didn't know that that was what I was going to do. So maybe I give him more credit now than I did at the time because I didn't know what I was doing. But mainly my thesis advisor is the main one. And then when I got here, the thesis supervisor was at MIT and his name was Arthur Kerman. And when I got here, I worked with Ernest Henley, who was a famous professor, and he also did things the right way in terms of character and personality. And then one more with my postdoctoral advisor, Leonard Kisslinger at Carnegie Mellon University. He's very enthusiastic and filled me with enthusiasm.
And then were there any pivotal moments in your research career that made you change topics or want to pursue a certain topic?
I've been working in doing physics research for 50 years, so there have to be many, many changes of topics because you can't do the same thing for 50 years. Generally, what caused me to change was some new experimental development that I wanted to participate in, a new experimental challenge. I guess it was a dozen years ago, there was a new set of experiments in atomic physics, which I hadn't worked on, which potentially showed something amazing. Basically, that Coulomb's law was wrong. Coulomb's law says the thing that determines the force is the product of the charges and nothing else matters. But there were some indications from atomic physics that was not the case, and that would be a big deal. And so that was an exciting field. It turned out that those indications were wrong, but it was fun to find out.
And then where do you see your research field expanding to? So, like, what are some interesting topics that can be further explored within the next 10 years?
Well, 10 years is a long time scale for me. I'm 77 years old now. You're talking to someone, I'm still very enthusiastic, but I'm nearing the end. I'm still doing good work. However, I'm lately changing my field entirely to condensed matter physics, which is in its simplest form, it's a study of things that are around us. Why are some things solid? Why are some things liquid? What are the underlying forces? I think this has a greater chance for practical applications in the work I've been doing. So it's also fun to work on something totally new. So that's what I'm doing mainly now. We'll have some obligations to projects that I have to finish.
And then, like, what different institutions have you worked at, and how were those experiences?
My grad school was MIT. That was great. It was a very exciting time. A lot of interesting visitors coming into the department and interesting fellow graduate students. Then I went to Carnegie Mellon University as a postdoctoral researcher. And that was also an exciting time. There were some new accelerators that were opening up, and I helped to analyze and predict certain experiments that were being done there. And at Carnegie Mellon, there was a great group of people who worked on those new accelerator things. Then I went in 1975 here to the University of Washington, where I've been ever since. I've worked in a lot of different research places on sabbaticals. I've been to CERN in Geneva. I've been back to MIT several times. I've been to Los Alamos National Lab and also Jefferson National Lab, which is in Newport News, Virginia.
Okay. And then how did you find your passion for research, and how would you suggest someone else try to find their own passion?
I guess it was really that I liked certain courses in physics and I wanted to keep doing it. And I kept enjoying it the more I did. And I went to grad school primarily because I knew I didn't know anything about physics. So I went to grad school and I really loved doing the homework problems. And I thought that's what I wanted to continue to do.
And then, like, what kind of skills do you think a high schooler could develop, even if they don't have access to a lab or any of the tools that you guys have?
Yeah, well, I'm a theorist, so I basically need computers, a little bit of paper. That's about it. Fortunately, well, we might not be there yet, but m most people have access to computers, and you can do an awful lot of calculations using computer programs. I guess it would be you can develop technical schools using the tools that you have. You don't necessarily need a big lab. Take advantage of anything that's available if somebody in the high school is doing experiments. When I was in high school, there may have been opportunities, but I didn't know about them. I guess I was just getting through high school. But it was one of the premier high schools of science in the world. I didn't know I wanted to be a scientist, so I didn't do too much. So I think just to use the resources that you have in whatever school you're in. The main thing is to find something that you like doing. The work is hard enough so that if you don't like doing it, it's just not worth it. Everybody has to find what they like. Like my parents wanted me to become a medical doctor, but I just didn't like the courses related to doing that. And there were other aspects too that made it not for me.
Yeah, okay. And then what traits do you think define a great researcher in their field? And like what type of traits would you look for in a potential lab member or collaborator?
Enthusiasm and technical talent. For me, it means can you do math? Can you do math related to physics? The enthusiasm and drive is also very, very important. If a student is not interested, and I can perceive that, then I won't work with them.
And then I'm sure that you get a lot of emails from different students asking to like join your lab or just work with you. But how do you pick someone out from like the crowd? So like what makes a student stand out to you?
I usually take everybody, almost everybody, as long as if they have the initiative to come and talk to me, I'll at least talk to them and give them a chance. And usually I pretty much take everybody. There aren't that many, so it doesn't take up too much time. But if I'm working with a student for a while and they're struggling and they can't do things that are needed to succeed, to make progress, then I will tell them it's not working and to find something else. But that happens rarely.
And then just for a final question, what kind of advice
Mhm.
would you give to a high schooler who wants to go into physics?
Learn as much as you can. Keep learning. Read as much as you can. Get good math skills. Just learn as much as you can as soon as you can in physics and related subjects, especially math.
Okay, so that's all the questions that I have for today. And thank you so much for
Okay.
meeting with
You're
me.
welcome.